Is it recording? And it's in focus? Excellent. Welcome to Math372 Complex Analysis, Lecture 31, give or take a little bit. We're going to do SES forms. Could you close the door? Thank you. We're going to do SES forms later today, so I wanted a topic that I could do in on the order of 30 minutes to leave you plenty of time. The slides are online, as well as a slightly longer version of the talk which I gave at Williams and Mystic. If this gets out of focus, I'm going to trust the people in the way back to just tell me something to move a little bit. All right, what I want to do is just continue the theme of the end of the semester of applications of complex analysis. We worked really hard at the beginning of the semester proving a lot of results. Where does this stuff all go to? All right, so the main idea is to understand two extremely important papers from the 1960s. And this is the, how's that? All right, two extremely important papers from the 1960s. The first is by Lorentz, determining non-periodic flow, and the second is by Mandelbrot, how long is the coast of Britain? Out of curiosity, how many of you have seen either of these papers? Okay, good. So the first one is the famous butterfly effect, that weather is chaotic. And so just from the conclusion of the first, all solutions, and in particular the period solutions, are found to be unstable. When our results considering the instability of non-periodic flow are applied to the atmosphere, which is ostensibly non-periodic, they indicate that prediction of the sufficiently distant future is impossible by any method unless the present conditions are known exactly. So the way Lorentz discovered this is he was trying to reproduce some simulations he had done, and he had run them, and then he wanted to look at some part again. And so he just, rather than starting at the very beginning, he just inputted where he was after a certain amount of time. And very quickly, the results were markedly different from what had happened before. And what was going on is I think the computer was printing out the results to 3 digits, but internally was keeping things to 6 digits. And this led to the idea of extreme sensitivity to initial conditions, that very small tweaks very rapidly lead to wildly different behavior. For a lot of things, a small tweak is not going to make a huge difference. If you're throwing a pitch, if you release over here versus over here, there's not going to be much of a difference. But for a lot of the stuff in physical systems, very small changes in initial conditions rapidly lead to wildly different behavior. The other one from Mandelbrot is geographic curves are so involved in their detail that their lengths are often infinite or rather undefinable. And so the question is, what is the dimension of the coastline of Britain or other countries? Now, we're used to dimension being an integral quantity. Dimensions are either 1, 2, 3. Could look at maybe an n-dimensional space. We've done enough mathematics that we're fine with that. He actually calculated, this is going to be, let me try to do it like this. Well, is it adjusted well? I'm going to just leave the clicker over there and just yell. Okay, so Britain had dimensions about 1.25. The land frontier of Germany in 1899, 1.15. The Spain-Portugal land boundary, 1.14. All the way down to South Africa, which does a really nice job at 1.02. So what do we mean by these dimensional numbers, and how do you calculate them? What is the link between the two papers? As I've been saying numerous times, extreme sensitivity to initial conditions. Okay, so let's talk a little bit about dimension. So this part I'm going to go a little bit quickly. Anybody want to define dimension for me? This is the we all know what dimension is, but how would you define it?
I mean, I don't know exactly how to define it, but isn't it related to like how many parameters it takes to describe any point?
So one suggestion was it's the number of parameters needed to describe a point. Okay, but we might have more than a point. We might have an object. So maybe the number of parameters we need to describe an object. This seems to be implying an integral notion. What does it mean to have half of a parameter? But it turns out that a lot of the concepts that we use, it's very hard to define them well. And this is one of the big things, if you read Euclid's geometry, Euclid's elements, how do you define the basic building block concepts? Which ones do you want to be the basic building block concepts? So here, since this is a math class, we're fine with this one. I won't say how well this went over at Mystic. Hausdorff dimension. So take some subset of Rn, so x1 through xn. If we dilate S by a factor of R, let's say that gives us C copies of S, then the dimension D of S satisfies R to the D equals C. All right, so let's do an example. So here's a segment of length 1, laser pointer should work, and for those of you who will someday buy laser pointers, you want a green light because the green light records much better than a red light. Sadly, I learned this only after buying red light once. So let's dilate this by a factor of 3. We now have 3 copies of the segment. So we're trying to solve r to the d equals c, I equals 3, c equals 3, so d must be 1. So we get that a line segment has dimension 1. Building on this remarkable success, we move up to a square. And we have a square. If we increase the sides by a factor of 3, we now have 9 squares. So when we're trying to solve r to the d equals c, we get 3 to the d equals 9, so d equals 2. Here it is nice and red. And so we have a 2-dimensional object. In the interest of time, I'm not going to draw the 3-dimensional or 4-dimensional objects on the planar surface. All right. How many of you have seen the Cantor set? Okay, so everyone's seen the Cantor set, so I'm going to do this really rapidly. So we basically keep throwing away the middle third, you keep throwing it away, and then the question is, what would be the dimension of this set? And so if we dilate by a factor of 3, so we start off almost like this and increases by a factor of 3, we would get 2 copies of the set. And so we end up trying to solve r to the d equals c, so 3 to the d equals 2, so d is the log of 2 base 3, or about 0.63. Does that number seem reasonable? Okay, so why is it reasonable?
Because there's a bunch of points there. It's not all gone, but
it's not all gone.
Yeah.
So we've got something, and it doesn't seem as solid as the entire line segment. So it seems reasonable. It should be somewhere between 0 and 1. So whenever you're doing math, you always want to get a sense of, is my answer reasonable? Now, for those of you who maybe have done real analysis or measure theory, you can also start doing fat Cantor sets, where instead of removing the middle third, you remove different things so you can actually have something with measure left. And there's a lot of interesting games you can play. Pascal's Triangle, this is a fun one. So each entry is the sum of the 2 above, and you just have 1s going along the diagonals. Let's modify Pascal's Triangle. Let's put a dot if n choose k is odd, and make it blank if it's even. So the 1 by 1 Pascal Triangle is just a dot. The 4 level would be the following. And to do a little movie, so I wrote a Mathematica script a couple of years ago to do this. It was just easier for me to have Pascal's Triangle on its side rather than vertical, just the way the things were. And I'm also adjusting it so that it's always taking up the same space in the square. So I'm just rescaling things as I go. Otherwise, of course, this would be expanding, and all the construction on campus is not enough to give me a big enough blackboard for what I want to do here. I couldn't find something like this on the web. I can adjust how quickly it's playing. It's playing at a slow rate in the beginning. I would probably want to speed it up here. It's a very interesting question as to how would you program this to display efficiently? And how would you calculate the binomial coefficients efficiently? And so if you want, that's a really good question. If you only need, say, this coefficient here, what's the fastest way to calculate just that coefficient? And you also have to worry about overflow. If you're on a very old calculator, if you're taking huge factorials, there's going to be problems. Okay. So here's just a couple of the images. And then, of course, this is related to some fractals. So you might have seen Sierpinski's triangle. And if you just rotate your head 90 degrees, you should see that basically these are the same. And then, nice exercise to prove this. What do you think the dimension should be here? Oh, before you give me the answer, tell me something about the dimension. It should be between 1 and 2. We're definitely getting a whole solid side, so it's at least 1. We're losing some stuff. It's probably not as high as 2. So when you have something like this, what would you want to scale by? And how many copies would you get? We're trying to solve r to the d equals c.
Scale by 2.
Yeah.
3 copies.
Yes, if you take this and you scale by 2, then you get 3 copies. So the dimension should be the log of 3 base 2, about 1.58. And as an exercise, prove that 1.58 is between 1 and 2. All right, not too bad. All right. So how else could you generalize Pascal's triangle? So I'm going to just leave you some links if you want. Here's what the pictures look like. If I now start doing, instead of dot or blank, that's really looking at things mod 2. You can look at things mod 3, mod 4, mod 5. And you can just ask, what kind of patterns do you get? Okay, let's pivot now to coastline. And so the coastline paradox is the measured length of a coastline changes with the scale of the measurement. So it led to the following. So L of G will be the length, and G is the scale of our measurement. So imagine you have a rod of fixed length G, and you're going to put it down, then pick it up and put it down. And you're going to march all the way down the coastline. Initially, maybe your stick is 200 miles long. And if it's 200 miles long, you're not going to be able to see a lot of subtle ins and outs. And then you would expect, as your stick gets shorter and shorter and shorter, you should get a better and better measurement. Do you think you'll always be more accurate? So I'll leave that as an exercise. If you change the stick by an arbitrary length, will you always have a more accurate measurement? This goes back a little bit in calculus when you did partitions to do Riemann sums. Is a partition with more points always closer? Or is it sometimes not as close as the previous? And then this is why sometimes when we do refinements, we always double the number of points and put something in the middle. So it's not just a generic shuffling. So it's a nice exercise. Do you always do better? And so this is a couple of examples of changing the size. And over here, we're using 200 kilometers, 100 kilometers, 50 kilometers. And you see the length is changing significantly from 2400, 2800, 3400. So as an example, how many of you have seen the Koch snowflake? Okay, good number. So start off with a straight line, and then remove the middle third and put in an equilateral triangle, but don't include the bottom side. Now we have 4 line segments. On each line segment, remove the middle third, put in the equilateral triangle, and keep iterating. All right, and so as you do the calculation, the area is going to be finite. As a nice exercise, you can prove it's contained in a circle of a given radius. But the length is infinite. It doesn't intersect. It's a really nice curve. And you can see that when you go from one level to the next, you increase the length by a factor of 4/3. So it's very easy to figure out what the length is at every stage. All right. So I want to now get into chaos. This is the real part where complex analysis is going to come into play. It's also going to allow me to talk a little bit about some applied math. I know some of you have heard this from me in other classes, but it's worth repeating. So, not surprisingly, we like to solve equations in math. Okay? So here's some examples. Linear equations, not a problem. Quadratic equations, not a problem. Cubic and quartic equations, not a problem. And so the story I've heard is that hundreds of years ago, you could challenge people for their math position, and you would give them a set of problems, and they would give you a set of problems. And if you could do theirs and they can't do yours, you get to change positions. I'm not sure if it's true. I kind of like the story, so I haven't really checked. And the story I've heard is that the person who came up with the formula to solve the cubic just kept that in strategic reserve, so that whenever they're challenged, they will just give you, well, here, solve these 10 cubics. And without knowing the formula for the cubic, there was really no good way to do that. And so it's just a way to have good job security. Almost surely the story is false, but it's a fun story. It's up there with, did I tell you the stealth bomber story? So that the story almost surely not true is when they were trying to design the stealth bomber and stealth fighter, they were trying to maximize stealthiness, and they forgot to check the second derivative, and they just looked for the critical point, and they actually built the we're here plane. Almost surely not true, but nice stories to just illustrate the dangers of points. How many of you have seen the formula for the cubic? How many of you can prove the formula for the cubic? There's a lot of really good math about how you find the formulas for the cubic and the quartic. And a lot of it is you go through these auxiliary polynomials. And what happens is once you get to a polynomial of degree 5, when you try this process, you actually get back at some point a polynomial of larger degree than you started. It doesn't prove that the method won't work, but it should be enough to scare you. It turns out that there is not a formula for quintic and higher. You often prove this in either an abstract algebra class or a Galois theory class, one of the nice gems of mathematics. This doesn't mean that a polynomial of degree 5 doesn't have roots. We proved in this class, fundamental theorem of algebra. Polynomial of degree n has n complex roots. It just means we can't write them down in closed form. Closed form expressions are wonderful. If I want to see, well, what would happen if I change this parameter b? How would the roots change? Well, very easy to figure this out. When you're modeling things in the real world, when you're trying to decide how I want to allocate resources, it's nice to have closed form expressions. Frequently in economics, we don't have stuff like this. We have to resort to Monte Carlo simulations, to numerical simulations, to try to get a sense of what's happening. All right, here are the three roots of the cubic. Now, what's fascinating is you have i's. And so it could be the case that all of the roots are real, but you still need to have the square root of -1 to find them. You could also have roots that have legitimate imaginary parts, and then the I is not so surprising. Here is the first of the 4 roots for the quarter. A lot of this is you can do things to make things a little bit nicer for yourself. So, for instance, see how we have b's over here. I can adjust things to get rid of the x cubed term. If I subtract the right thing from x and then I expand, I can make the cubic term from here cancel the cubic term from there. And if you do something like that, you will simplify a lot of your expressions over here. So frequently you want to make some of these transforms initially and then do the analysis. This is very similar to a lot of times in complex analysis we'll say, well, without loss of generality, let's assume we have a circle centered at the origin. And then maybe we can adjust the scale so it's of radius 1. All right, so let's talk about solving equations in general. Imagine I give you a continuous function, and at 0 and a little bit after 0 it looks like this, and at 1 and a little bit before 1 it looks like this. What do you know is going on in this region marked by 5 question marks? Has to cross. Why does it have to cross?
This is continuous.
Okay, be more specific. So it's continuous, so what does that allow us to use? Not the mean value theorem. The intermediate value theorem. So a nice consequence of the intermediate value theorem is the mean value theorem. So the intermediate value theorem says that if you have a continuous function and it's, say, value c1 here and c2 here, then it takes on every value between c1 and c2 at least once. Maybe multiple times, but at least once. And if you think about it, well, if the function is continuous, if it always stays below 0, how is it going to jump up over here? This is essentially there are no transporters for continuous functions. Okay? We don't know how many times it crosses. We don't know where it crosses. If we're trying to find where it crosses, if we want to solve f of x equals 0, how can we do this? Well, the first method is divide and conquer. So let's assume f is continuous. Let's assume f of a is negative, f of b is positive. Then f has root between a and b. What we can do is look at the midpoint. If the midpoint is 0, yay, we're done. If not, if it's positive, then there must be a root between f of a and between a and the midpoint. If it's negative, between the midpoint and b, and then just lather, rinse, repeat. Just keep doing this again and again and again. So for example, if f of 0 is -1 and f of 1 is 3, we can look at f of a half. If f of half is a 2, then we know there's got to be a root between 0 and a half, so we try a quarter. And we keep going on and we keep going on. Okay, I thought that's as far as I went. So this is a nice method. If I want to gain additional degrees of accuracy, however, how rapidly will this gain for me? So how does the error change as I keep iterating?
Doesn't it just happen?
So it halves each time. So initially, I had an interval of length of length 1, then I had an interval of length 1/2. So every iteration, I have my error. So 2 to the 10 is 1024 is almost 1,000. Are there any CS majors here? Okay. So it's not that the CS majors don't know their Latin and their Greek. When you say how many megabytes are in a gigabyte, if you look at the words, mega to giga should be a factor of 1,000. But for computers, we look at things in base 2. So this is why if you actually look at files being, large files being downloaded, it'll be writing it in megabytes, 950, 960, 979, 999, and then it will go to like point something with a gigabyte. For all practical purposes, however, 2 to the 10 is really very close to 1,000. So essentially, every 10 iterations gains you 3 decimal digits of accuracy. So if you wanted to 6 digits, you would have to do this on the order of 20 times. So we're trying to approximate the square root of 3, which is about 1.732050807568887, etc. And you can see after 10 iterations, we're somewhere between 1.7304 and 1.734. So it's not horrible. We've got about 3 decimal digits, which is what I told you we should expect. So it's a lot of work. But all we need to do is evaluate the sign of the function at that point to use divide and conquer. That's a huge advantage. We don't have to actually evaluate the value. We just need to know, is it positive, negative, or 0? Right? How many of you have seen Newton's method? Okay, and this is what's going to lead into the complex analysis. So assume f is continuous and differentiable. We're going to generate a sequence of points that will hopefully converge to the root as follows. Given some point xn, we'll look at the tangent line to the curve at xn. It has slope f prime of xn, and it goes through the point xn f of xn. So we can write down the tangent line, and then we can see where does this tangent line hit the x-axis. So we would set y equal to 0. That gives us our new point xn plus 1, and then just lather, rinse, repeat. So just drawing it, here's our curve, y equals f of x. Here's my initial guess to the root. I'll call the root a. Here's my initial guess. I draw the tangent line at the point, and I see where the tangent line approximates the curve. This is not perfect. Locally, however, this is pretty good. And this is the main point, or one of the main points of calculus. A complicated function is well approximated locally by a straight line. And this goes back to the mean value theorem that was just taken a moment ago as a suggestion. That's essentially a first order Taylor series. And the idea is, if my function was exactly a straight line, if I just follow the straight line, that would be the root. Well, it's not the root because it's not a straight line. But then we just lather, rinse, repeat. Then we'll come up over here, we'll draw the line, and we'll intersect. Which do you think is a better method, Newton's method or divide and conquer? I'm sorry?
Newton's method.
Okay, why is Newton's method better?
Well, because it'll be faster.
Okay, so it turns out Newton's method is a lot faster. This was actually the problem that converted me from physics to mathematics. I was a double major at the time, and then this was assigned as, it was problem 16 from chapter 3 of Rudin was square roots. Problem 18 was pth roots. Problem 17 was another method that wasn't as good as that wasn't as good as Newton's method. And I was just floored at how well this converges. And so let's talk about how well it converges. So for instance, let's say f of x is x squared minus 3. If we go through and actually write down the equation of the tangent line and find the point xn plus 1, we can solve it in terms of xn. This is just algebra. And you get this wonderful formula. Xn plus 1 equals 1/2 xn plus 3 over xn. So you give me a point, and I actually have a rational expression for the next one. So I'm not just getting an approximation. I'm getting a rational approximation. And I don't have to evaluate my function at weird points. I don't have to do complicated things. Now again, I'm using the very special function f of x is x squared minus 3. So the first thing you should always ask when you see a formula like this is this reasonable? Are there any consistency or sanity checks you can do on this formula?
Well, you can see what it is if you take the limit.
Okay, so how would you take the limit?
Just, if you call the limit L, you just solve L as 1/2 times
Okay.
L plus 3 over L.
Okay, good. So if the limit exists, which we don't know it exists, then we would try to solve, L equals 1/2 L plus 3 over L, and you would get a quadratic equation. And hopefully, that would reduce to x squared minus 3. So that's a good thing to do. What else could we try?
X and 0.
I'm sorry?
X and 0 would give us a problem.
X equals 0 would give us a problem. Now, that problem is related to something that I have hidden. This is an incomplete plot. The plot should continue like this and come up. How many roots are there to x squared minus 3 equals 0? 2, right? And so if you're at 0, this is going to be a spoiler alert for later in the talk, but if you're at 0, which root do you want to go to? This is like asking a parent which kid is your favorite. Well, given that one of my kids had a meltdown today, it's actually a very easy question today. But in general, we try not to answer questions like that. So imagine you are 0. Which root should you go to? Isn't it nice that this is undefined? I'm sorry, I just can't choose a root. I'm undefined, not taking sides. So if you put in 0, there will be a problem. But there's another sanity check you can do for this. Or there's a few others. And this is more important than the applications of math, is looking at formulas and seeing are they reasonable. What could we do?
I mean, you could put the root in.
Yeah, put in root 3. If we put in root 3, we get root 3 plus 3 over root 3. 3 over root 3 is root 3. Root 3 plus root 3 is 2 root 3 divided by 2 is root 3. So it's a fixed point. A fixed point is a point where when you apply your map, you get back where you started. You can basically convert almost any equation, finding f of x equals 0, to finding a fixed point by looking at a slight tweak of the initial problem. So this is good. If we start off at the root, we stay at the root. Excellent. You could also try, well, what would happen if I put in something greater than square root of 3? Does it get closer to the square root of 3? What if I put in something positive but less than the square root of 3? Does it move up? And so you can try all these different things. What I want you to get in the habit of is whenever you see a formula, whenever you derive something, whenever somebody gives you something, check and see if it's reasonable. One of my students from Brown many years ago was working in an investment company and just something didn't seem right. Turns out they had a minus sign in the wrong place. It was very good that this was found before they did a significant investment. But you want to get a feeling when you look at math, is this reasonable? And that's why I really want to spend time hopping on stuff like this. All right. So here's a couple of approximations. Here's the square root of 3. Here's the 5th iteration. And I've put in slight bold the first digit where they differ. And this is starting with my initial guess as 2. All right. 2 is not a bad guess for the square root of 3, but it is not a terrific guess. I'm not stacking the deck. Newton's method, basically, every time you iterate, you double the number of decimal digits of accuracy. So if you look at what's going on, absolutely amazing how quickly this converges. So which would you rather use, Newton's method or divide and conquer? Are we all converts to Newton? Is there any reason why we might not use Newton's method? Yes?
It might not converge.
So one thing is it might not converge. Will the divide and conquer always converge?
Yes.
Divide and conquer will always converge. So this goes back to, it's nice to know you'll get the right answer. Yeah, this could be the hare versus the tortoise.
It also might not be differentiable.
It might not be differentiable. So the divide and conquer, all you need is a continuous function. Newton's method, you need a continuously differentiable function. So the input is much stronger for Newton's method. So depending on what you have, you will use different techniques. It's not surprising that if we have more information, we should be able to converge faster. We're now using more facts about the function. I was going to say those of you, I'll say, well, for those of you who've taken a probability class, you might want to compare Chebyshev's theorem versus the central limit theorem. And the more you know about your distribution, the better convergence you can have. All right. So here is the game. It's kind of been spoiled because of a comment from earlier, but here's the equation x squared minus 1, and I've factored it so that you don't have to do this on the fly. So the roots are 1 and negative 1. And I'm going to color them red and blue. And now, what happens as we iterate? Where do you think we converge to?
So it depends on where you start.
So it depends on where we start. So when do you think we iterate to red?
When x is less than 0.
So when x is less than 0, we iterate to red, and when do we iterate to blue? By symmetry, it should be when x is greater than 0, and 0 will not take sides. I probably should have made a purple dot there. Game seems pretty boring, right? All right. But this is a class in complex analysis, so we can make the game a little bit more interesting. Let's take x cubed minus 1 equals 0. We had such great success with x squared minus 1. So the roots are complex numbers. So you can go through. You actually don't need the full strength of the cubic formula. If you notice that, well, x equals 1 is a root, I can do polynomial long division, or I can just remember that I can use the quadratic formula, and we get our 3 roots. So here are our 3 roots in the plane. So we have the red, the blue, and the green. And I want to apply Newton's method. When do you think we should iterate to the blue? When do you think we should iterate to the red? when do you think we should iterate to the green? Yes.
I would expect slices that are thirds.
Okay.
Playing.
And how do you determine which third to take? What's the rule? Because there's infinitely many ways I can slice this into equal thirds. There's a nice clean way of describing how you slice.
I would think with each point in the middle of its slice.
Okay.
60-degree angle slices.
Like this?
Yeah.
Okay. So I think the easiest way to say this is these are all the points that are closest to red. These are all the points I think closest to blue.
Yeah.
These are all the points closest to green.
Yeah.
Seem reasonable? This is what you get when you apply Newton's method. So if you've never seen this before, something is wrong. This is not what you would expect. This is the extreme sensitivity to initial conditions. What's going on in here? Well, this is just some issues with just the resolution. Does this make sense that you have this huge patch of green, huge patch of red, huge patch of blue? Yeah. But then the fascinating part is as you get over here, all of a sudden, you iterate down to the blue. And so what I will do is I will play the clip. So this one actually doesn't have the funky, crappy music. But this is just zooming in as what's going on. And not surprisingly, they've chosen to zoom in on the origin, which is the most interesting piece. And the behavior gets really fascinating. And as you start to get in closer and closer and closer, what is it looking like?
Oh wow. There get to be more slices.
Yeah, so it gets up to 6 slices. But you still have these rings coming in. And so, okay. So just to end, Mandelbrot set. So it's all complex numbers such that if we consider the map f of c of u is u squared plus c, then the sequence of iterates remains bounded as n goes to infinity. The points that remain bounded is the Mandelbrot set. The points that are unbounded, that go off to infinity, is the complement. And we color the points differently based on how rapidly they go off. All right. So here is the standard Mandelbrot set. It's fascinating looking at some of the original pictures of the Mandelbrot set on old computers. They didn't have enough resolution to see a lot of things, and they thought actually there were maybe some disconnected components. So let me see if this video.
I think this has the cheesy music.
Yes. So this one has the cheesy music. Okay. Most of them put in some kind of soundtrack as you're zooming in. And so we're heading to one point over here. And just an incredible, and look at how much we're zooming in, a factor of 10 to the 275. And so there's always the question of which point do you want to zoom in. I'll just go until we start to see at least one Mandelbrot set as we go in. I wish they actually were showing over here how much you've zoomed in as you go along. And so and then you can ask, how do you actually do calculations this precise? Because we have extreme sensitivity to initial conditions. How can you trust the output that's coming? So you need really good ways to do these evaluations. Here it's coming. Here we go. There is one. Oh, lost it. I'll just zoom to the end. I might be able to be prosecuted for psychedelic mind control right now. You will take more math. And just as you zoom in, there's another copy, and essentially the game can go on and on and on. It's extreme sensitivity to initial conditions. Just a couple of famous pictures of it that I'll put in. This is where we ended. A couple of links. Quick consequences. Why do we care? If small changes can lead to such wildly different behavior, what happens when we actually try to solve equations. So one of my friends works at a think tank, and he actually found some flaws in climate models that were being used. In fact, what he discovered was they were making some bad assumptions, and also the models were so sensitive to the initial conditions that depending on what policy recommendations you wanted, you just had to change parameters by infinitesimal amounts, and then you could have the simulation support whatever you want. So there is enormous opportunity for, I'll leave it as opportunity. These are the weather equations. I'm not going to go through the details of this, but again, it's a system with extreme sensitivity. And just two places that start off very close to each other, but very quickly diverge as to where they are. Takeaways: math is applicable, which hopefully you've seen numerous times. You now have enough techniques to solve some real problems, or to convince people they can't be solved. We see very similar behavior in wildly different systems, and this is where your training is wonderful. I've written papers in accounting, marketing, economics, computer science, geophysics, sabermetrics, statistics, marketing. I've lost track of how many different fields I've worked in because I'm trained as a mathematician. My favorite was applying some number theory into a marketing problem. The last is the different kinds of challenges. So I want you to think about how would you calculate these iterations for the Mandelbrot set as to what's going on well enough to be convinced that this should be colored this way versus something else. Okay, so this is a good place to stop. If you could turn off the camera.